make the same frequency that was the natural or resonant frequency of the glass. And so, and then they had recorded her on tape, and they played tape with another glass there, and it broke. And they said, "See how great our tape is at reproducing, you know, frequencies." So that was a little more.
It was Etta Fitzgerald, wasn't it?
I don't remember who it was.
Yeah.
It was somebody that could sing really hold a long note, because she had to get it so she'd see it vibrate. Did you guys ever watch CSI New York? Where, who is that? It's not Gary, is it Gary Sinise,
Yeah.
right, in that? There's one episode of that is again going back 5 years or more, but the one with the ladies that's from Tiffany's, did you guys see that one?
I didn't see that.
Okay, well, anyway, these three ladies, they're dressed up like Audrey Hepburn was in Breakfast at Tiffany's. They have raincoats on, they have a shopping bag, they have a little hairdo, which is a wig actually, but it's got like a little beehive, you know, and they have sunglasses. And the three of them are walking along the street in New York, okay? And they come to the jewelry store, and they turn in the jewelry store. The first one goes in, and she walks to this end of the store. The second one comes in, and she walks to that end of the store. And the third one comes in, turns around, locks the door, and takes a shotgun out of her bag and just says, "Everybody, hit the floor." All right? And they do. Now, this is a jewelry store. It's full of these cases. The lady on this side takes some kind of a device out of her shopping bag and turns it on. And you don't hear anything, but all of a sudden, all the glass in the display cases shatters. All right? And then these two ladies, they pick up that little device, and they go and they just pick up all the jewelry that's in there, and then they leave, okay? So tell everybody to stay on the floor, and they leave and quickly take off their disguises and get away. And so Gary Sinise has to figure out what happened, and of course, glass is not really that uniform, all the different pieces of glass, but what he figured out was the electronic device they had was a high-frequency generator, all right, of a sound wave, but too high for people to hear. And what they did is they cranked it up so that all the glass in the cases shattered, and then they could just pick up all the jewelry out of the display cases and walk out. So that's just an example in case you ever see an old CSI New York with the ladies walking with their shopping bags. That's the whole story, and that's how he tracks them down. But anyway, that's resonant frequency, all right? And so I've given you a couple of examples of that now. So with the bridge and this and that walkway over the lobby. Okay, the interference of waves, we already talked about that. It can be constructive or destructive. And if it's destructive, this is like what the pilots have in their earphones that they have, where it's destructive. The sound of the engine is here, and then they generate a wave electronically that counteracts it. But you can also get the sound to be louder by having constructive interference. So, but we already talked about that. This is somewhat repetitive. Ultrasound. You have a problem on this too in the homework. That's a high frequency wave. Again, we can't hear it, and it's going to be somewhere in the neighborhood of 1 to 5 million cycles per second. Remember that capital N always means million. So it's really, really a fast, very high frequency. And the thing to remember about this, and read the section in your book on this, but the point here is that the ultrasound probe, like, you know, if you want to look at an embryo or fetus, for example, when they put that on the woman's stomach, what's happening is the ultrasound probe is sending a wave out that strikes the object and then reflects back and gets picked up. It gets detected when it gets back, and then the electronics in there can sort out the image. The things to remember, and this will be helpful in doing that problem, is that the depth that you can get is about 200 times whatever the wavelength is. Now remember, the speed of the wave is going to be, they have to tell you that. I don't think I have it up there. No, but it's about 1,500 meters per second is the speed of that wave going through tissue, going through water, tissue. And so knowing the speed and knowing the frequency, let's say you pick a 5 megahertz or a 2 megahertz, that will be able to, by figuring out from that, using that equation where we have 1,500, okay, equals, right, say 2 million times the wavelength, you can figure out what the wavelength is from that. It's the same equation we had at the very beginning. And so, once you know the wavelength, 200 times the wavelength is how deep you can go. Okay, so the bigger the wavelength is, the deeper you can go. The shorter the wavelength, the more shallow that you would go. Because you would use a different frequency if you were saying, if you wanted to say, look at a baby, right, that's in the mother's stomach, or you wanted to find a little piece of metal that was in somebody's eye, for example, if they had an accident. You would want to use a different frequency. The other thing is that the size of the object that you can see with the ultrasound probe is the smallest you can see is about 1 wavelength, which is really small, I mean, really tiny. So, but you guys can see that they, based on how deep they want to go and how much they want to be able to resolve the image, they will choose the proper frequency here for the probe. Okay, so that's how that works. And now let me see. This was, I guess this is actually an example in your book. Let's take a look at that. It's on page 235. Okay, it says, ultrasound has a speed of 1,500 meters per second in tissue. A, calculate the smallest detail visible with 2 megahertz ultrasound. Well, this is where you can jump down and see what they did there. They said the speed and the solution, the speed is the frequency times the wavelength. So the wavelength is then going to be the speed divided by the frequency, and you can see you come out with a really, really small number for the wavelength. And so the smallest detail is going to be about that same distance. So that's what I tried to show you up there. The smallest detail is going to be about 1 millimeter that you can see. Rounded, it's about 1 millimeter. How deep did you go? Well, it's going to be 200 times that, that wavelength. So it can tell you the depth that it will penetrate is about 0.15 meters, which is 15 centimeters. That's about, 15 centimeters is about 6 inches, okay, in terms of depth. And then it says that part C was, how long does it take the echo to return to the probe from a depth of 0.1 meters? Well, that's just going to be distance equals the speed times the time. Here's the distance, here's the time, and then you have to remember in this case to divide the time by, the echo return. You have to divide this time in half, because remember, for an echo, the sound wave has to go out and strike the object and then come back. So it's you only need half of that distance, okay? So you just have to take that into account there. But they explain this in the book, but I just thought it might be better if you guys actually see see it worked out a little differently than they did. And superposition of waves, we already talked about that. Now, when 2 waves have just a slightly different frequency, all right, you hear what's called a beat frequency. This is what happens when, if you go to see a band, perform. For example, they'll have the band members come out, and the lead guitar will usually come out, and he'll, he or she will play a note. Okay, what they'll do is they'll be playing a note that's a particular frequency. Let's say it's a typically, I guess they would say a middle A is about 440 cycles per second. So they'll do that. So if let's say Brandon was the lead guitarist, and so he plucked that note, then I would take my guitar. Maybe I have the rhythm guitar, right? He's got the lead guitar. So the rhythm, I would pluck that same wire and listen. Now in the audience, you don't hear any of this because it just sounds like noise. But if that's you hear your A and his A, and they better be the same. And if they're not, you have to tune your instrument quickly to get it so that you only hear one note. Now the beat frequency is something that when you're off a little bit, it will sound like you hear those 2 notes, but you'll also hear overlaying them, something like that. It's called the beat frequency. And that tells you you're not exactly in sync. So you have to tune yours until that beat frequency disappears. Okay, if I remember, I'll bring in some tuning forks next time. You can see, if you guys can actually try it and hear a slight difference. Another example is if you're at the, a little related to this, if you're at a traffic light, like you're turning left, and so you get in the left turn lane, and you have to wait for the light, and your blinker's going on and off, right? So your blinker's going on and off. If the car in front of you has their blinker on, do you ever notice where sometimes they're coming on and off together, but then they get out of sync? You ever notice that? And then they'll come back into sync? That's the same idea as the beat frequency, when you're out of sync a little bit. You just need to adjust to get so that you're exactly the same. So the way you calculate the beat frequency is just what's the difference in the two frequencies. So for example, if Brandon played the 440 and mine happened to be a 442, I would hear a beat frequency. When I was listening to it, I would hear a beat frequency of about 2 per second. Something like that is what I would hear. And then I would have to retune that and quickly retune the rest of the guitar, all right, or whatever other instrument you have. Everybody does it at once. In an orchestra, it would be what they call the first violin. If any of you guys go to those kinds of concerts, then you know, a classical concert, they'll come out and the first, and everybody will blow out the first violin, come in, you know, play that one note, and then everybody else sets their instrument. And although today they probably do most of that pretty accurately with electronics now, where you can set it before you even go out. We talked about the resonant frequency.